everyone. How you doing? Hope everyone's doing very well. Hope you are 1, washing your hands. Hope you are 2, maintaining social distance. And then number 3, staying in the house. Don't go anywhere. Just take it easy. Relax. Do your homework. Continue to study. That's very important. Well, here we are. Remote learning at its finest. There will be an AP examination this year. It's going to be only 45 minutes. It's going to be, there's not going to be multiple choice. It's going to be free response questions. Probably 3, 4, maybe 5 questions. I'm not certain. And it's going to be online if we are not in school. If we are in school, we return back to school, guess what? Still going to be online. Okay? So we want to pick up where we left off. We were talking about sequence and series. And before we left, here are the series that we did cover. Okay? We covered the nth term test for divergence. We went over the geometric series test. We looked at the p-series test. We covered the integral test. We looked at the direct comparison test. We looked at the limit comparison test. And we also looked at the telescoping series test. So this 1, 2, 3, 4, 5, 6, 7. There are 7 tests that we already looked at, we've already gone over, we've already explained, practiced with those 7. However, there are a couple of more that we have to look at and to explain. One we're going to do today, which is the alternating series test. Look at that, 1. And 2, we have to take a look at the ratio test and the nth root test, but those are in our next lessons. Today we just want to look at the alternating series test. So what I would like for you to do, pause the video right now and copy down the notes, and then I'll be back to go over the examples with you, okay? Okay, so I'm going to now move to the right. I'm back. All right. Hopefully you've copied down the notes. Let's get into it. Okay. Alternating series test. Here's what the series look like. As n equals 1 all the way up to infinity, the series is defined by -1 to the power of n. This lets you know it's alternating, because for every odd power n, we're going to have a negative coefficient. For every even power n, we're going to have an even number coefficient. So it goes negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, back and forth. All right? Or it can be expressed as n equals 1 to infinity, -1 to the n minus 1, such that when n equals 1, we're going to get -1 to the power of 0, which is 1, positive. So this series right here is going to start positive, negative, positive, negative, positive, negative, so on and so forth. Whereas this one right here, it starts off negative first. Negative, positive, negative, positive, negative, positive. And if that's happening, what is it doing? Yes, it is alternating. That's why this is what defines an alternating series. All right, here, point 1. The sign of each term alternates. All right, point 2. Here are the conditions for convergence. There are 3 of them. If all 3 conditions are met, we can conclude that the series converge. Condition number 1, an is positive. That means that our sequence a of n is greater than 0. So this sequence right here, a of n, this sequence must be a positive sequence. Okay? No negatives there. It must be positive. If a of n is positive, then we're good. Condition 2, an is decreasing sequence. So what does that mean to decrease? Well, that means that 0 is less than a of n plus 1, which is less than a of n. This means that each succeeding term must be smaller than the preceding term. Okay? So, as n goes into infinity, each term that follows is smaller than the previous term. It must be decreasing. All right? And you can show that, or what you can do, you can find the derivative of the sequence, an. And the derivative has to have all values that are less than 0. In other words, as n goes to infinity, a prime of n, its derivative is less than 0, negative. And we'll show that as well. And then if condition 1 is satisfied, the second condition is satisfied, the third condition also must be satisfied. And that's that you have to show that the limit as n gets very large and goes into infinity, then the sequence itself, a to the n, actually equals 0. Show those three conditions, we have convergence. Right? Check it out. Failure of any condition. That's why this arrow's here. Bop, bop, bop. Failure of any condition renders the what? Test inconclusive. You can't determine anything. You don't know if the series converge or diverge. Missing or failure to qualify by missing the mark with any of our conditions. Okay? All right. Now, let's take a look at these examples and see if they meet all three conditions. Okay. Example 1. Here we go. So the first thing I want to do with this series, I want to rewrite it like this. So this equals summation n equals 1 to infinity of -1 to the n times 1 over n. So now this explicitly lets you know what a sub n is. All right? So this right here tells me that a sub n equals 1 over n. -1 to the power of n, that just lets us know we're alternating, right? We're alternating. Negative, positive, negative, positive, negative, positive, negative, positive. We do have an alternating series. All right, so an is actually 1 over n. There's our sequence right there. 1 divided by n. Okay? So now let's go ahead and check out three conditions. Condition 1. First condition, right? Says that a subscript n, which is 1 over n, where 1 over n has to be greater than 0. Well, is that true? Let's see. If I plug in 1, I'm going to get 1 over 1, and then 1 over 2, and then 1 over 3, and then 1 over 4, and then 1 over 5, dot, 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 to 1 over n. All these values are greater than 0. Nothing negative. Condition 1 is satisfied. Okay? Our sequence is all positives. Condition 1 is satisfied. Condition 2. Now, condition 2 states that a and n must be decreasing. This means that all subsequent terms, or succeeding terms, has to be larger than the preceding terms. Okay? A subscript n plus 1 has to be smaller than a to the n. So if n equals 1, then a subscript 2 has to be less than a subscript 1. So the succeeding must be smaller than the preceding, right? So let's look at it. So here we have a1. Here we have a 1 plus 1. Well, let me write that as n plus 1. Here we have this one as a, n plus 2, so on and so forth. All right? So when n equals 1, here's our first term. When n equals 1, here's our second term. When n equals 1, here's our third term. And notice how our terms, the succeeding term, is greater than the preceding term. In other words, 1/2 is definitely less than 1. Decreasing. Notice how, okay, 1/3 is less than 1/2. Decreasing. All right, and also we can keep on going. It's decreasing, just like 1/4 is less than 1/5. Decreasing, and on and on and on and on and on and on and on. Okay, so you get the idea. So this right here satisfies condition number 2. Okay. All right. So condition number 2 is satisfied because what we have a decreasing sequence. If you wanted to use calculus to prove or to show that the sequence is decreasing, no problem. All right. Take a look at the series, which is A of n. That's another way to write it. A of n equals 1 over n. By the way, A subscript n is the same thing as A of n. They're the exact same thing, right? So A of n equals 1 over n. Take the derivative. A prime n equals negative 1 over n squared. And you can see whatever values you put in for n, starting with 1, right there, you're going to get negative 1, right? If you put in 2, you're going to get negative 1/4. You put in 3, negative 1/9. So as you can see, it satisfies this point right here, that the derivative of an is always less than 0. So we satisfy condition 1, we've satisfied condition 2, and now onward to condition 3. Okay? So with condition 2, back at condition 2, we can say negative 1 over n squared is less than 0. It's less than 0. Okay? Of course, where n cannot equal 0, of course. Well, n is never 0 because we're starting with n equals 1. All right, condition number 3. Condition 3 says that the limit as n gets very large, an has to equal 0. Okay? Well, let's see if that's true. Well, the limit as n approaches infinity of 1 over n is 0. Because as n gets very, very large, 1 divided by a large number gets very, very close to 0. As n gets larger, 1 over n gets increasingly smaller, and it approaches 0. So all 3 conditions are met, which lets us know that this series is convergent. So we can conclude that the series as n equals 1 to infinity of negative 1 to the n over n is convergent. It converges. Okay? All right, let's take a look at our next sequence, a series. Let's see if our next series is going to converge. All right, so now we have the series n equals 1 up to infinity of negative 1 quantity power of n divided by n factorial. Okay. Well, first off, let's take a look and see. What does our sequence in this case? We can rewrite it. N equals 1 to infinity of negative 1 to the n. It alternates. Times 1 over n factorial. So a to the n is 1 divided by n factorial. All right, and we know that factorial implies multiplication. In decreasing order or increasing order, it does not matter which way you go with it, because multiplication is commutative. 4 times 3 times 2 times 1 is 1 times 2 times 3 times 4. So it doesn't matter which way you go. All right, so an. First thing we have to do is determine whether or not it's positive. Well, 1 over n factorial is greater than 0 for all n greater than or equal to 1. How do you know that? Well, because 1 over 1 factorial is 1. 1 over 2 factorial is a half. 1 over 3 factorial is 1/6. And so on and so on and so forth. So all of our terms are going to be positive in that sequence. Okay? So condition number 1 is met. Condition 1 is a go. Condition 2. Well, with condition 2, I would take a look at the sequence. As you can see, it is decreasing. We go from 1, then down to a half, then down to a 6. Okay? And the larger the denominators get, the smaller the fraction is. Large denominators, it's going to give me a smaller fraction. So that means that 1/2, of course, is smaller than 1. 1/6 is smaller than 1/2. And so on and so forth. Okay? So condition 2 is satisfied. So A of n is decreasing. Because A subscript n plus 1 is less than A of n. So it is decreasing. All right. Condition number 3. The limit as n goes to infinity of 1 over n factorial. What is that? What is that limit? Well, one thing we have to recall is what we call the growth comparison factor. The growth comparison factor, which says that here's what it says. Logarithmic functions is going to be smaller than our polynomials, which is going to be smaller than our exponentials, which is going to be smaller than our factorials. And the factorials are going to be smaller than our variable exponentials. That's the comparative growth factor. So, log functions grow slower than polynomials, polynomials slower than exponentials, exponentials slower than factorials, and factorials slower than the variable exponentials. Okay? Which states that the limit as n goes to infinity of the slower over the faster is 0, and the limit as n goes to infinity of the faster over the slower is infinity. So what do we have in this case? 1 represents a polynomial or an algebraic function, because 1 is the same thing as 1 times x to the power of 0. That's a polynomial. So I got a polynomial divided by a factorial. And a polynomial divided by the factorial is like saying something that grows smaller over something that grows larger. So we have the smaller or the slower divided by the faster or the larger, which is going to take us to 0. So that means that all 3 conditions are met. All right, so our series here, this series converges. This series converge. We met all 3 conditions. How about our last series? Convergent or divergent? Okay? Well, first, let's rewrite it. And if we rewrite it, we can rewrite it as such. N equals 1 to infinity of -1 to the n times 3n over 4n minus 1. All right, so that's first. Let's check our conditions. Condition 1. Is it positive? Is 3n over 4n minus 1 greater than 0? Well, for every value of n you plug in, well, when n is 1, you're going to get 3 over 3, which is 1. When n is 2, you're going to get 6 over 7. When n is 3, you're going to get 9 over 11. When n is 4, you're going to get 12 over 15, so on and so forth. For all values n, yes, it is positive. For all values n, plug it into the sequence, we're going to get a positive value. Condition 1 is met. Condition 2. All right. So condition 1 is met. Condition 2. Is a n decreasing? That's the question. Well, let's take a look at it. Let's look at our numbers. Let's see if it's decreasing. 1, 6 over 7, 9 over 11, 12 over 15. Are these numbers getting larger or are they getting smaller? Okay? Well, if you compare these first two terms, all right, 6 over 7 is smaller than 1. It's not exactly 1. So I decrease there. If I compare the next two terms, 6 over 7 and 9 over 11, well, 9 over 11 is smaller. Well, how do you know 9 over 11 is smaller than 6 over 7? Here's how you find out. Here's what you do. All right? You take 9 over 11 and you take 6 over 7. And I'm saying that this term 9 over 11 is smaller, less than 6 over 7. Here's how you check. If you take 7 times 9, that is 63. If you take 11 times 6, that is 66. And since 63 is less than 66, this implies that everything on the left side is smaller than what's on the right side. So 9 over 11 is smaller than 6 over 7. All right, so 9 over 11 is smaller, and likewise with 12 fifteenths. 12 fifteenths is smaller than 9 elevenths. So we can conclude that yes, our function is decreasing, okay? Or what you could have done if you want, you don't necessarily have to, you can use calculus, right? You can use calculus. If you use calculus to show that it's decreasing, if I were to use calculus, then I would have an equals 3n over 4n minus 1, such that a prime of n. Find the derivative using the quotient rule. Low d high minus high d low squared below. Okay? My derivative is going to be low 4n minus 1 times the derivative of the high, which is 3, minus 3n times 4, all over 4n minus 1 squared, which is going to give us, what is that, 12n minus 3 minus 12n, all over 4n minus 1 squared. Notice the 12n's cancel out. 12n's go, and that's going to leave me with negative 3 over 4n minus 1 quantity squared. There you go. No matter what value you place in for n, when n is 1, n is 2, n is 3, n is 4, no matter what value you place in for n here, you're going to get a negative number because of that negative 3 right there. It's going to be negative. So you can prove it with calculus or without calculus that our series, well, our sequence rather, A subscript n, it is decreasing. All right. Now let's go to our third and our final. So we know we're decreasing. Let's go to our third and final condition here. All right, the limit as n goes to infinity of 3n over 4n minus 1. What does that equal? Well, if you notice, the power in our numerator and the power of n in our denominator is the exact same, n to the power 1. So this is just going to equal our coefficient, which is 3/4. Uh-oh, we have a problem. Because that's not equal to 0. It says the limit has to equal 0. That limit is not equal to 0, which means the test is inconclusive. Absolute convergence does not mean that this series right here diverges. Here's what absolute convergence tells us. Absolute convergence tells us this. If the series as n approaches 1 to infinity, absolute value of an, if this converges, then the series from 1 to infinity of a to the n converges. That's all it tells us. That's it. If the absolute value of the series diverge, this test tells us nothing. We don't know. So here's what we do know. This series does not absolutely converge. It does not. Therefore, what we have is we have conditional convergence. So when you said that the series converge, be sure to go back and put this word next to it. It's conditional convergence. It converges conditionally. Does it absolutely converge? No. No. All right? So does the series converge? Does it converge? Yes. Is it conditional convergence? Yes. Is it absolute convergence? No. It does not absolutely converge. Because when I put absolute values around it, it diverges because of the p-series. No absolute values around it, it will converge, and it converges conditionally. Okay? How about the next one? Let's see what we get over here. Let's see if it absolutely converges. All right, let's take a look at it. Okay, so we're going to have n1 to infinity, absolute value of -1 to the power of n over n factorial, which is going to give me the series as n goes to 1 of infinity of 1 over n factorial. Okay, what's going on with this thing? Does this converge or does it diverge? Which one is it doing? All right, well, let's try this first. If I take this right here, if I try the nth term test for divergence, what will I get? The limit as n goes to infinity of 1 over n factorial. What does that equal? That's going to give me 1 over what? 1 over infinity, which is going to give me 0. So this test is inconclusive. That test is inconclusive. So that's not telling me whether it converges or diverges. Furthermore, you could use the growth factor here. You have a polynomial over the growth factor here, and the growth factor, the polynomial over factorial, and the growth factor here also says that it goes to 0. Okay? And so, what I would do now to teach you whether or not this converges or diverges is use what I call the not the nth root test, the ratio test. I will use the ratio test, which I haven't gotten to yet. I haven't taught you the ratio test. So I'm going to write use the ratio test to determine absolute convergence and so I'll come back to this one regarding the absolute convergence of that, because I haven't taught you the ratio test yet. And maybe I shouldn't even use this example to test for absolute convergence, because I haven't taught you the ratio test. So I'll come back to teach you absolute convergence on that using the ratio test. Okay? For this one, we don't have to check this one because we know that one's divergent. We don't have to check. All right. So this one we'll come back and we'll grab it and we'll see if it absolutely converges once I teach you the ratio test. Because you want to use the ratio test, right, when you have factorials and when you have exponential powers. You use the ratio test. So I will teach you that in our next lesson. All right? So we know it converges. Does it converges absolutely? Stay tuned. We'll come back to that. And that's pretty much everything regarding the alternating series. Make sure our 3 conditions are met. Okay? If one of them fails, then the test is inconclusive. Okay? Then it's not going to converge. Then that means that the test is inconclusive. You got to go find another test. Like right here. This test was inconclusive because our 3rd condition did not work. So I had to use another test, which was the nth term test for divergence. Okay? The alternating series remainder theorem. What does that mean? The alternating series remainder theorem. Here it is. Given the conditions and restrictions for an alternating series, we can estimate the sum of the series when, here we go, when the absolute value of S minus Sn is less than or equal to a to the n plus 1. All right? This is the alternating series remainder theorem. All right? Where this S here, this in actuality is the sum of the series. Sn represents the partial sum of the nth term. And an plus 1 right here, I want to call this the first term that is not included in the partial sum. Okay? This is the alternating series arraignment theorem, which is used for alternating series. Here's what it does. Here's what it does. It gives you, and I'll write it up on the board for you. Here, write it up on the board for you. Here's what it gives you in essence. It gives you the partial sum is within, there it is, a specified range of the actual sum. That's what it tells you. The partial sum is within a specified range of the actual sum. So if you don't know the sum of a series, and it's an infinite series, so you're not going to know the sum of it. But the partial sum, right? Along with, here's the partial sum, the nth partial sum, along with the first term not included in the partial sum, okay? This right here tells you that the partial sum is within this amount right here of the actual sum. The partial sum, here's your within, is within this amount. Within of the actual sum. That's the range. This is how close the partial sum is going to get you to the actual sum. It's going to get you this close to the actual sum. Let's do an example. Let's check it out. It's pretty simple. It's not too bad. All right, here we go. For example, in fact, let me come over here. Let me write it up on this side. Let me erase all of this. Here we go. Example. Let's say we have series n equals 1 to infinity, -1 to the n plus 1 of 1 over n factorial. Okay? And let's determine the estimation of the sum using the, let's use the sixth partial sum. You don't have to use the 6th partial sum. You use the 1st partial sum, the 6th partial sum, the 12th partial sum, it doesn't matter. Okay? The more partial sums you use, the closer and the better your estimation will be to the actual sum. But you can choose, or whatever the instructions say. I'm going to use the 6th partial sum. Okay? I'm going to use the 6th partial sum. So first, let's determine what the 6 partial sums are. All right? So S6 equals, well, here we go. If you plug in 1, you're going to get 1. Plus, plug in 2. Okay? When we plug in 2, well, it's going to be a negative. It's going to be minus. Plugging in 2, we're going to have 1 over 2 plus. Plug in 3, we're going to get 3 factorial, which is 1 over 6 minus. Plug in 4, we're going to get 4 factorial is 4 times 3 times 2, 24. 1 over 24. So we got 1, 2, 3, 4 plus. What's the 5th term? 5th term is going to give me 5 factorial over 5 factorial. 5 times 4 times 3 times 2 times 1, I think that's 120. 1, 2, 3, 4, 5 plus, nope, minus. 1 over 6 factorial. What is 6 factorial? Need a calculator. I don't know. 6 factorial is 720. Alright, so I have my first 6 terms. Alright. Term 1, 2, 3, 4, 5, 6. Find the partial sum. That means do the calculation right here. So the 6th partial sum is going to be, I have it written down right here, add it all up. You get 91 over 144, which is approximately 0.63194. All right. That is your 6th partial sum. So with the 6th partial sum, watch this, that's the value that goes right there. So if I structure this, if I set it up, this means the estimated sum of the series is the absolute value of the actual sum minus the partial sum of the first 6 terms, which is that 0.63194. All right. Which has to be less than or equal to. This is the succeeding term after the 6th partial sum. Okay? So after I get the first 6 terms, 1, 2, 3, 4, 5, 6, plus, watch this, plus an plus 1. That's right here. And that is the 7th term. That's what this represents, the 7th term. And what is our 7th term? Let's see. A7 equals 1 over 7 factorial, which is, I have it written down, all right? 1 over 5040, which is equivalent to 0.00019. All right, and that's what goes right here. 0.00019. That's not bad. That's pretty good. Yeah. Because what this tells us, ladies and gentlemen, is that our estimation after finding the sixth partial sum, the sixth partial sum puts us within this amount of the actual sum of the whole entire series. With the sixth partial sum, this is how close we are to the actual value of the series. That's not bad. That's really great. In essence, here's another way to write this. Another way to write it is like this, that 0.63194 minus 0.00019 is less than the sum of the sequence n equals 1 to infinity of -1 to the n plus 1 times 1 over n factorial, which is actually less than, all right, so since it's with n, I got the difference on one side and the sum on the other side, which is less than 0.63194 plus 0.00019. So the actual sum of the whole entire series is within this range right here. It's within that range, okay? And so that's what this remainder theorem tells us. This estimation remainder theorem tells us that we can get very close to the actual sum of the entire series by looking at a partial sum as we go along the way within the series. Sixth partial sum, seventh partial sum, eighth partial sum, doesn't matter. Whatever partial sum you want to use, you're within the range of the entire sum by using the magnitude of the succeeding term after the nth partial sum, whatever you use. And so there you go. That's how you find it. All right? So using the sixth partial sum in this case, it puts us within this amount of the actual sum. And that is read as, how do you read this? Let me see. Tens, hundreds, thousands, 10,000, 100,000s. That puts us within 19 hundred thousandths of the actual sum of the entire series. And that is the alternating series remainder theorem. Okay. All right, so that's going to do it for our alternating series tests. We're going to come back and we're going to go over the root test. And when we do the root test, we're going to get back to our problem that we had to show absolute convergence. That's coming up next. And so until then, stay tuned, visit the Google Classroom. I will download all the lessons there, and all the assignments are also going to be in the classroom. All right? Till we meet again next time, take care, be good. Stay safe, social distancing, stay home. And if you have any questions, cares, concerns, worries, woes, you can email me through the classroom, or you can email me on Outlook and let me know that way if you have any concerns. Okay? All right, guys. Till we meet again. Be good. Bye-bye.